Assalamu alaikum warahmatullah. So, in this video, we are going to discuss another important question from chapter 2, that is electric potential. So, the question here says there is a 5 marker. The question here says define electric potential, derive expression for potential due to an isolated point charge at a point. Yeah. So, first thing is he has asked for defining the electric potential. What do you mean by electric potential? Electric potential at any point, let me just dictate. Electric potential at any point in electric field is defined as work done in carrying a unit positive charge from infinity to that point against the electric field. Okay, so it's simple. I repeat the definition. Electric potential at any point in an electric field is defined as work done in carrying a unit positive charge from infinity to that point against the electric field. So basically electric potential का मतलब होता है कि the amount of work done in carrying a unit positive charge from infinity to the point where we want to find the potential, and obviously it has to be against the electric field. Okay, so the definition I hope you can understand. Now let's move forward with the derivation. Okay, let us say charge O, charge is placed at O. Okay, and I need to bring another charge, yeah, or I need to find potential at P, which is at a distance R from the charge. Okay, so what we do is first we try to consider some point A, and we try to move through a small distance, say A to B. Let us say the distance is dx. Okay, and from infinity to bring A, then from A to B we try to find the work done, then the amount of work done will be stored as potential energy. So this is from the work energy theorem. Let us say point A is a distance, is at a distance of x. Point A is at a distance of x. So let me quickly tell you the initial explanation, initial introduction for this. Consider a point charge plus q. As I read, I'm marking. Consider a point charge plus q. Consider a point charge plus q at O. Okay. After that, let point P be a point at a distance r from the center O. We have marked. Electric potential at P is the amount of work done in carrying a unit positive charge from infinity to point P. Electric potential at point P is nothing but the work done in carrying a unit positive charge from infinity to point P. So this is what we are trying to find. So the first line says we need to give the introduction. Consider a point charge plus Q at O. Let P be a point at a distance R from O. Then electric potential at point P is given by the amount of work done in carrying a unit positive charge from infinity to the point P. Okay, so to do this, what we do is, after writing the initial introductory line, then you tell consider some intermediate point, consider some intermediate point A at a distance x. Okay, so this is the initial introductory part for the derivation. Okay, so once you consider point A at a distance x, first we try to write the electrostatic force. Yeah, the electrostatic force on unit positive charge is, what is the electrostatic force on unit positive charge? We are considering the unit positive charge at point A, isn't it? So the electrostatic force, or should I say the electrostatic force on point A, or unit positive charge is given as E is equal to 1 by 4 pi epsilon naught q by x square. Yes, and this is along OA. This is along OA. Zahir si baat hai, this is the positive charge. Electric field will be outwards. So for point A, the electric field will be this way. We are considering unit positive charge here. What is the electric field at this particular point is given by E is equal to 1 by 4 pi epsilon naught q by x square. I hope this point is clear. Okay. Now once you're done with that, what we do is we try to find out from the diagram itself what is the small amount of work done in moving that unit positive charge from point A to point B through a small distance dx. So we'll write small amount of work small amount of work done to move unit positive charge from A to B through distance dx. So that will be given by a small amount of work dw is equal to, we'll be writing actually work done is equal to force into displacement. Force is nothing but E is equal to F by Q. We know from this another E is equal to F by Q basic. So F is equal to EQ. So this becomes W is equal to EQ times S. Q is unit positive. So it is E into distance moved is dx. So we write here dw is equal to E dot dx. E dot dx, which is E dx cos 180, which gives rise to minus E dx. Okay, E dx cos 180. Why cos 180? E is outward along BA and dx movement is against the electric field. So this negative sign clearly shows that we are moving away. We are moving against the electric field. That's what it shows. Okay, so negative sign, what it shows, that also you can write. Yes, work is done against, or you can say E and dx are opposite in direction. Yes, both can be told. Now, after going through this much, what is the total work done? Total work done in moving the same positive charge, moving unit positive charge from infinity to point P. So now we have got one general expression, dw is equal to minus E dx. For that same thing, we will be writing minus E dx infinite, integrating from infinity, point P is at a distance r. So this will be the equation. This comes from what we have cleared out here, dw is equal to minus E dx. So once you do this, the next step is just integrating infinity to r, and minus E can be written as 1 by 4 pi epsilon naught q by x square times dx. So after writing so much, it's just simple integration from here. What we will do, minus q by 4 pi epsilon naught integral infinity to r. What is remaining? 1 by x square times dx. 1 by x square means x bar minus 2, isn't it? You know the integration of x bar n plus 1, sorry, integration of x bar n. Integration of x bar n is x bar n plus 1 by n plus 1. So using that, this will be x bar minus 2 plus 1 by minus 2 plus 1, basically minus 1 by x you get. So you just substitute that, minus q by 4 pi epsilon naught and minus 1 by x, okay, with the limits infinity and r. So once you do that, what do you get? Minus and minus goes away, q by 4 pi epsilon naught you get, and upper limit 1 by r minus 1 by infinity. So this gets cancelled. You get the final equation as w is equal to 1 by 4 pi epsilon naught q by r. This is what you get. And the last, you can say work done is nothing but from work energy theorem you can write, and simply write from work energy theorem, work done is stored as potential energy. So you can write V is equal to 1 by 4 pi epsilon naught q by r. So this will be your equation for the question that has been asked. So I hope you have understood the question. I'm just repeating it once, just go through what we have done. Initially we define the electric potential. What is the electric potential definition? Electric potential at any point is defined as the work done in carrying a unit positive charge, work done in carrying a unit positive charge from infinity to that point against the electric field. So that is your definition. After that we came to the diagram. In the diagram, how did we learn it? We considered a point charge at O, let point P. be a point at a distance r from the center. Electric potential at P is the amount of work done in carrying a unit positive charge from infinity to point P. So this we have understood. Next, what did we do? Consider some intermediate points A and B, and let us say we move the charge from A. Okay, so unit positive charge. What happens is, what is the electric field? What is the electrostatic force on the unit positive charge when it is at A is given as E is equal to 1 by 4 pi epsilon naught q by x square. Then what is the small amount of work done? What is the small amount of work done in moving a unit positive charge from A to B through a distance dx? dw is equal to E dx. By using this particular basic, I have shown E dx cos 180, that is minus E dx. Once you get that, the total work done in moving the unit positive charge from infinity to point is given by, actually you can write here, dw is equal to minus E dx first, then you integrate both sides, then you come to this step. Okay, so write that from infinity to r the limits were put, and finally you simply did the integration part and you got the answer, and finally you told work done is nothing but energy stored. So work done is shown as potential. So this is the derivation. Yes, or you can write this as work energy theorem, or you can do a thing, you can write it in another way, that is from the definition. From the definition also, we have just from the definition, this will be easier. From definition of electric potential, from definition of electric potential, we have already told what electric potential is: the work done to move the charge from infinity to point. So clearly work done can be written directly as V from the definition of electric potential. So I hope this particular derivation is clear. Thank you.